Professor Saul Teukolsky,
Okay.
which is here. Yes.
Yes.
Hello. So, can you share the screen?
Just share my screen.
Okay.
Okay, you see that?
Yes, we see that. And okay, so so the next talk, as I said, from Professor Saul Teukolsky from Cornell University, and they will tell us about testing No-Hair Theorem and area theorems with LIGO. And yeah, whenever you're ready, you can start. And do you have a timer, or do you want me to give you a heads up, 5 minutes?
I'll keep track.
Okay, perfect.
You can cut me off if I forget.
Yeah. Okay,
Okay.
you can start. Thank you.
Thank you. So let me start first by acknowledging my collaborators on this project. So firstly, Matt Giesler, who the work I'm going to describe involving quasi-normal modes and overtones was done by Matt as a graduate student, my graduate student at Caltech. And then the data analysis of LIGO Data, that part of the project was mainly led by Max Easy as a postdoc at MIT. Okay, so let me start with this famous picture from Kip Thorne, drawn long before we could actually solve Einstein's equations numerically for merging black holes. And it shows the three divisions of the merger process: the in-spiral, where the waveform can be essentially predicted by post-Newtonian theory; the merger, where the post-Newtonian approximation breaks down, we need full numerical solutions of Einstein's equations. And then after the two black holes merge and form a single distorted black hole, we have the ring down phase, where the radiation is dominated by these quasi-normal modes that I'm going to be talking about. And eventually we settle down to a final Kerr black hole. And just sort of on a personal note, I find it kind of amusing. My PhD thesis was to work out how to study analytically this ring down phase. And now I'm come full circle to work on this again. All right, so let me remind you about the first gravitational wave event detected by LIGO. And the conclusion I want you to take away from this is that it's all very well to talk about deviations or alternative theories of gravity to general relativity. But actually, general relativity, if it's wrong, it's not wrong by a lot. So for example, this is from the discovery paper. The top plot that's shown, I don't know if you can see my cursor here. The top left plot is the signal from the detector at Hanford. This signal has been superposed on the right on the blue signal from Livingston. You don't have to do fancy data analysis to see that, that they agree pretty well. That tells us it's an extraterrestrial event. In the second panel, there's some smoothing has been done on the data, some filtering of the noise. And so the red here is a numerical relativity simulation that fits the data very well. This was done by our SXS collaboration. And then if you look carefully, you'll see a sort of a gray band underneath there with a little width. And that represents the smooth data up here with some error bars on it. And by eye, it agrees pretty well. If you subtract them, you get the bottom plot, which is the residuals. And basically, the residuals are consistent with Gaussian noise at about the 4% level. So very crudely, you've got 4% to play with if you're looking for deviations from general relativity, at least in this particular event. And one of the very first tests that the LIGO science collaboration did with this data was a consistency test. From the early part of the waveform, you can deduce the initial masses and spins of the black holes up to some errors. And then using the numerical relativity simulation, so in other words, you're assuming general relativity is correct, you predict the final mass and spin, MF and SF. And then you just look at this exponentially falling decay of the waveform from the peak down, and you fit a quasi-normal mode, a damped sinusoid to that. It has a frequency in a ring down, and assuming that this is given by a perturbed Kerr metric, you can deduce the final mass and spin just from the frequency and damping time. And they agree pretty well, as we'll see in a minute. Okay, so let me talk a little bit more about quasi-normal modes. So we have this famous aphorism of John Wheeler, a black hole has no hair, to describe this fact that a stationary black hole is described only by mass and spin, right, the Kerr solution. And here I'm focusing on astrophysical black holes, so I'm assuming that any charge is rapidly neutralized by plasma and will be very small from a gravitational point of view. So the idea of the no-hair test goes back several decades. The idea is, suppose you have a gravitational wave detection, and you're able to measure at least two of the quasi-normal modes. So presumably the two least damped modes that will survive the longest. You then have four numbers that you've measured because you have a frequency and a damping time from two modes. And if the solution is a perturbed Kerr metric, then those four numbers you've measured should be consistent with a single value for mass and spin. And so that's the idea behind testing the No-Hair Theorem. And when this idea was first proposed, people did estimates of what kind of signal to noise ratio you would need, how strong an event you would have to have in order to actually carry out this test. And the predictions were quite pessimistic, at least as far as LIGO is concerned. The expectation was that you would have to wait for what's now called third generation detectors, or possibly even LISA, which will fly in space, hopefully in the 2030s. And the surprising thing is that this expectation was wrong. And let me show you why. Okay, so let me quickly, this is the only slide I have that has equations on it. Let me remind you a little bit about Kerr perturbations. So we'll focus on this quantity psi4, Newman Penrose scalar. It's basically just a component of the Weyl curvature tensor. Because the Kerr metric is stationary and axisymmetric, we can separate the variables with in the time coordinate and in the phi coordinate. It has a mutual coordinate. And then the surprising fact is that it also separates in the theta and r coordinates. Just for simplicity, I've written down the radial equation for this radial function for the case of Schwarzschild, right? And it's just the familiar Zerilli or Reggie Wheeler equation. Looks like a barrier penetration problem in quantum mechanics. And the relationship between this psi4 quantity and the measured gravitational wave strain, it's basically just a couple of time derivatives. And there's a normalization factor here depending on your conventions. But so basically, if you can calculate psi4, you can predict the gravitational wave strain that LIGO measures. Now, at late times, if you look at the solution of this equation, this r star, by the way, is the tortoise coordinate that just stretches out the horizon to infinity, stretches out that region to go from minus infinity to plus infinity. So at late times, you get the form of the solution. The radial factor is just an outgoing wave at large distances. So we have this particular form and then the angular value here. And we get these quasi-normal modes, right? They're like normal modes because we have boundary conditions at the horizon We have to have only ingoing modes. And at infinity, we have to have only outgoing modes at late times. And so that's an eigenvalue problem, and that determines there are only special omegas for which that is true. And the quasi-normal mode is because this is now a dissipative system, not conservative, we're draining energy, so the omega will be complex, right? And so we have this set of mode frequencies. And we can take the H and decompose it into spherical harmonics, which is the, I'm glossing over here, there's a distinction between these spin-weighted spherical harmonics and ordinary spherical harmonics that makes a few percent correction if you did this more carefully. So I'm going to simplify and ignore that for the purposes of this talk. So if we look at the modes that LIGO observers will actually use to analyze their data, I replace the S by a YLM, and then so the frequency will just be this superposition. These are the sum of the modes. Okay. Now, so the N here in this mode, so the LM are the spherical harmonic indices, and the N are just the labeling the eigenvalues of the radial equation, just like a radial quantum number. Okay, so the N, for historical reasons in this field, is called the overtone index. Okay, so the omega is a complex, a frequency and a damping time. The No-Hair Theorem asserts that you can calculate these normal mode frequencies, quasi-normal mode frequencies, just they depend only on the mass and spin of the final black hole. And by convention, N equal to 0 corresponds to the least damped mode. And then as you increase N, you get more rapidly decaying modes. Now, the name overtone is an unfortunate name that we're stuck with here, because to most physicists, when you talk about overtones, you think of them related to musical instruments or something like that, right? Where the N's describe multiples of a fundamental frequency, and they're usually subdominant compared with the fundamental tone. And that's just not true for black holes. And there's been the cause, I think, of a lot of confusion about the role of overtones. Okay, so let's go back to this first detection by the LIGO Virgo collaboration. So here's this consistency test that I described. Here's a plot of the frequency of the mode on the horizontal axis and the decay time on the vertical axis. And so the black sort of oval region in the middle comes from their full fit, right? The IMR is in-spiral merger ring down, the full fit that they did using the in-spiral part and the ring down part to get the values, the best fit values. And so you can think of it as this being the true measured values in the middle. And then they tried fitting a single damped sinusoid. And they found it was very sensitive to the start time that they used. If they used an early start time, so this is relative to the peak of the waveform. So if they waited, right, you're waiting for the nonlinearities, right, at the peak presumably corresponds to the strongest part of the merger signal, and where you would expect to have a lot of nonlinear effects. So you're waiting for that to decay away so you can see this damped sinusoid emerge. So this green region corresponds to waiting 1 millisecond after the peak. And you can see it's completely inconsistent with the true value. 3 milliseconds does reasonably well. You can see it here. Although, as you can see, it's biased, right? It's not centered on the true value. 5 milliseconds is better centered, but now you're in the noise. Your signal has decayed so much that the noise is dominant and you have a very big error bar. And 6.5 milliseconds on the scale, it's way off. You don't even see that. So you have this question, there's lots of literature, what's the optimum time to wait to do this test? Right, so at what point, after the peak of the waveform, do quasi-normal modes provide the correct description of this ring-down signal? And you have to be precise here because it makes a difference whether you're talking about the peak of psi4 or the peak of h. Remember, they're related by two time derivatives. And we're going to talk about the peak of h, and that's actually earlier than the peak of psi4. All right, and the surprising answer is you can actually do this. The signal, the ring-down signal, is a correct description or a very accurate description of the signal starting right at the peak, maybe even a little bit before, provided you include the overtones. Okay, and that's what I want to explain to you. Now, actually, Matt Giesler was not the first person to notice this. Back in 2007, which is the Stone Age as far as numerical relativity accuracy is concerned, Bonanno, Cook, and Pretorius showed, they looked at, I think at psi4, but same is true at h, that with the accuracy they had, they could use 2 or 3 overtones and get a reasonably good description close to the peak. This was used in the early EOB, effective one-body models of gravitational waveforms, to model the late time part of the signal. But then in order to match that to the in-spiral signal, which is dominated by the post-Newtonian, people developing EOB sort of bent things to match smoothly. They added some pseudo quasi-normal modes. And so most people who studied EOB correctly concluded that the description of the modes in the late time was sort of designed to be a fitting formula and didn't, they kind of forgot the motivation for it. And so that's the only explanation I have for why it's taken so long to rediscover this important feature of the waveform. All right, so let me try to convince you that you can go all the way to the peak with now here's remember, it's a linear superposition of quasi-normal modes. Okay, so let's focus on the 2-2 mode, which is the dominant one. So you just do a least squares fit. Let me see if I can hide this. Yeah, it's okay, sorry. So you do a least squares fit to this particular superposition of modes. Here, T0 is the starting time that you choose. So the least squares you're fitting, so let's assume general relativity is correct. We take a numerical waveform. So NR means numerical relativity. So we use the waveform that best fits the observed LIGO event. But we don't have to worry about noise. This is highly accurate numerical solution. And we try fitting various numbers of modes. So fitting the fundamental mode only, that's n equal to 0, that's the blue curve. What we're showing here is the mismatch, right? By how much does the model disagree with the full waveform? Right, and the mismatch is defined here just as a dot product, basically, right, and normalized so that this mismatch is 0 if we have a perfect fit. And you can see as we increase the number of overtones that we include, the mismatch gets better and better. And not only that, the minimum sets in earlier and earlier. And by the time we get to n equal to 7, you can see that we have an extremely good fit right at the peak, right? This 0 time corresponds to the peak of h. And there's nothing special about 7. If we had a more accurate numerical waveform, we could presumably keep going. All right, so the nonlinearities are small. The overtones is a linear description. And here I plotted them one on top of each other. The n equal to 7 model compared with the full numerical relativity solution. And underneath, I've taken the difference. And you can see that this residual here is above. The blue curve is an estimate of the accuracy of a numerical solution. And you can see that this is not some numerical artifact, right? This is actually telling us something. All right, here's my favorite way of looking at what's going on. We take the amplitudes that we found for each of the overtones, and then we plot a single line for each overtone. So we take its amplitude at t equal to 0, and then we multiply by the damped sinusoid, and on the logarithmic plot, that gives us a straight line. So the blue curve here, that's the fundamental mode, n equal to 0, right? And you can see that if you wait long enough, since it's the least damped mode, right, it's the strongest signal here, but you have to wait before that's true. The overtones, right, which we're used to thinking of as subdominant, they're actually bigger in amplitude than the so-called fundamental at the peak of the waveform. It's true that they decay more rapidly, but the early time signal is dominated by the overtone. And that's why it's possible to get a good fit, right? It's this early time signal which is telling us that the early part is dominated by the overtones, not the nonlinear. Now, you notice here that when does the fundamental mode become dominant? Well, this is in theorist units, 10M. 10M for the LIGO event is 3 milliseconds. So that explains why the LIGO Virgo analysis had to wait 3 milliseconds to see this thing. Now, when we first put this out, we got, a not altogether enthusiastic reception. Some people were a little irritated with us, I think, and thought there had to be something wrong. And so one of the criticisms or questions that was raised was, well, damped sinusoids are mathematically an overcomplete set. So aren't we just overfitting? Right? I mean, if you take enough basis functions, you can, as the saying goes, you can fit an elephant, right? So is there any physics here, or is this just overfitting? All right, so first of all, I'm going to argue that this idea of completeness is a red herring. The reason is quasi-normal modes arise as an asymptotic expansion. Basically, you can take any wave function, I put any in quotes, any wave equation, meaning that effective potential equation I wrote down for the perturbations, right, the V of R. If you have any equation of that form, provided the V of R satisfies some suitable fall-off conditions at infinity, then when you look at the Green's function, there will be an asymptotic expansion. If you look at it in frequency space, you'll have an asymptotic expansion where the poles in the lower half plane will correspond to the quasi-normal modes. So what we're really doing is, we are not doing an expansion, we're doing a fit. We're taking our knowledge that there has to be an asymptotic expansion, and we're fitting for the residuals at the poles in the lower half plane. Okay? And so we're just fitting for the dominant pieces of this asymptotic expansion. So fitting is not the same thing as making an expansion in a complete orthonormal set. Okay, so overcompleteness has got nothing to do with anything. The other mathematical result that seems to be at odds with this conclusion is there have been recent papers on the instability of quasi-normal modes. However, if you look carefully, these are related to the very high order, right, n large in that radial quantum number. So again, we're looking at the lowest 7 or 8 overtones, and I leave it to the more mathematically inclined to figure out where this instability is actually important. But it's, again, empirically not important for the low modes. So my attitude in this endeavor is that we should think of the mathematics here as an experimental science. And to show you what I mean, here's a plot of, on the vertical axis, the error defined in determining the final mass and spin from doing this fitting procedure versus the number of overtones that you're willing to include. So the thick lines here are just a repeat of the earlier fits that I did. And then this whole sea of different dashed lines and thin gray lines that you can see here, they come from different prescriptions for taking the analytic Kerr values of the overtone frequencies and perturbing them with positive and negative values here of this parameter delta. And seeing how, well, in other words, if it were really true that all you need is some random collection of damped sinusoids, and as long as you had enough of them, you'd get a good fit. Well, is that true? And the answer is no, right? A wide variety of perturbations, you always do worse than this line down here, which is the true solution with 7 overtones. So that's what I mean by experimentally, this is a valid procedure. All right, if you're curious about, is there something special about the particular numerical waveform that we use? Here's a test that Matt did on 80 waveforms from the SXS catalog, various spins and mass ratios and so on. And basically, this procedure seems to work at least, to an order of about 10 to the minus 3 or better. So there is something to understand here. What about real data? All right, so now let's move from now we put noise into the picture. So now we're going to repeat this idea of trying to do the fit, but instead of waiting 3 milliseconds, we'll start fitting at the peak. So this is real LIGO data that the LIGO Virgo collaboration has put out in the public domain. So the X is the center of the full in-spiral merger ring down. We can think of that as the true value of final mass and spin. So the dashed line includes the error bars, the black thing here. Now, just keeping the fundamental mode gives you this blue oval. So this is a repeat, a replotting of essentially showing what the LIGO people, why they had to wait the 3 milliseconds, right? They get a very biased value that doesn't even include the true value. If we add 1 overtone, we get the orange oval here, which includes the true value. If you try 2 overtones, it's a little less biased, but now you're starting to pick up the noise, so the error bars are bigger. You get a bigger area enclosed here. So I think that what the data tells us is the data is good enough to pick out 1 overtone, but you don't really do much better by adding a second. And so now you can try to do a test. So what we do here is we take this first overtone, so it has a frequency and a damping time, and we try to take the data and set bounds on deviations from the true Kerr values. So here is so we're adding additional parameters to the fit for the change in the deviation in frequency and the deviation in damping time. And so here's 0, no deviation. And the data, these are the bounds, these vertical lines, tells you that the deviation is 0 to about 20%. So yeah, it's not great, but I mean, the fact that you can actually, from the very first LIGO event, get any measurement, I think is quite remarkable, right? Unfortunately, the damping time is harder. There's no real bound here. It's 0 to, plus or minus order unity. What about the area theorem? So remember, the area theorem says that the total horizon area of black holes cannot decrease, right? So again, if we assume the Kerr formula for the area depends only on mass on spin. So the idea of this test is you try to get the masses and spins for the initial black holes and the final black holes, but you have to do that by separate measurements, right? It doesn't make sense if you're trying to test the area theorem, you can't, for example, take the initial masses and spins and then use numerical relativity to quote, measure the final ones, because numerical relativity assumes GR, so not getting much of a test. So the idea is you split H, the strain, at the peak time. You use only the early part of the waveform to get the initial masses and spins, and the final part of the waveform, the ring down part, to get the final mass and spin, just like we did for this overtone analysis. Okay. Now there's some trickiness in doing this. People had actually played around with this a while back and failed to get any good bounds. And the reason is, if you try to split, so this is H as a function of time. So if you try to split into two H's before and after the peak, when people typically do data analysis with real LIGO data, that's done in the frequency domain, right? Partly because the LIGO noise curve that you have to use when you do the data analysis is known primarily in the frequency domain. And also, you get to use all the fancy tricks of fast Fourier transforms, and the data analysis is much quicker. However, if you take a signal which, starts up here, so it starts at non-zero, and then decays away to 0, like this, or conversely starts from 0 and then ends at not 0. Those are not periodic signals. So if you blindly Fourier transform them, you get Gibbs phenomena, and your signal is contaminated by high frequency noise, and you can't analyze it. So this is well known if there are any experimentalists in the audience, but for the poor theorists who may not have encountered this before, there's a well-known technique for dealing with this. What you do is you take a window function or a taper. So think of multiplying, say, this signal by some kind of a signal which starts at 0 and then ramps up to 1, goes along at 1, and then falls off again at the end. Okay. And so what that does is it smoothly turns on the signal and gets rid of the ringing, the Gibbs phenomenon. Now you can see what the problem is. If you start your taper too late, so for example, if I started here at the peak and then go up, I'm losing the strong early part of the ring down signal, and then I'll just be dominated by this weak signal that's buried in the noise. If I move my taper to the left, so it starts early, then I'm contaminating the ring down with some of this early, of this late part of the in-spiral. So this makes it tricky to analyze. The answer is you just do the analysis in the time domain. And for those of you who are interested in how that's done, in the discussion section, I can explain why that's actually feasible on real data. So that's the point. You do this analysis separately in the time domain, analyze the in-spiral, analyze the late part of the signal, and here's the result. So I've plotted the probability versus on the x-axis here, this is the change in area, right? Computed from the final and from the early and the final black hole. So let's look at the green signal, the green probability that's including one overtone. And you'll see that there is a small probability here of a negative area change, but it's only 3%, right? So we can claim that the area theorem is valid empirically just from LIGO data at the 97% probability level, right? Better than 2 sigma. So again, you know, I don't want to make too much of you know, fundamental importance here in the sense that you know, I don't know how many people in the audience thought there was some serious probability that this theorem would be violated. You know, but still, I think it's cute that even with the first signal, one gets such a strong confirmation of the area theorem. And as we get improved detectors, you know, the signal-to-noise ratio of LISA for supermassive black holes should be more than 100 times what the signal-to-noise was of this LIGO event. And so we should get extremely strong tests of these kinds of things. All right, so let me summarize. Ring down begins at peak strain, right? Overtones dominate the early ring down and nonlinearities are surprisingly small. I don't think we really understand why that's true. Okay, so in observing the signal from infinity, the nonlinear processes that are going on right at that merger are screened out from the being directly observable at infinity, at least to very, you know, presumably you need much more accurate measurements to see, to probe what's going on in there. And, you know, there are other indications that this may be true, and there's some speculations to do with forming the effective potential outside the merging black holes and so on about why this might be true. But I think this is a fertile area for people to look at. And so the overtones enable a first test of the No-Hair Theorem and also a first test of the area theorem. Thank you.
Thank you. Thank you for this very interesting talk. And so let's see if there are some questions. So yes, okay, there is one question from an anonymous attendee. You kind of already answered, but let me ask anyway. So they ask how many overtones are needed to describe the ring down at the peak. I mean, you had a graph before.
Yes, so it's determined by the accuracy of the signal that you're trying to fit to. So for the numerical relativity waveform, which we can calculate to very high precision, we used 7 overtones plus the fundamental, and then we could get down to the numerical precision. There was nothing special about 7. If we had a more accurate waveform, we could have gone further. For the LIGO data, as soon as we start adding more overtones, we get cut off by the noise level. So there it turned out we actually only needed 1 overtone for the signal to noise for LIGO event.
Okay. Are there any other questions? Otherwise, I will actually be happy because I have some, but it's better if I wait and see if the attendees have any questions, you can just raise your hand and I will give you the word. Okay, seems not. I was just, I mean, you maybe already touched on this, but I was just wondering, this very surprising fact that the drilling down starts at the peak, right? And it seems to be really peculiar on black holes, because if I have a ultra compact object, for instance, and the quasi-normal modes will change completely, but the signal will not change, right? We'll have maybe some echoes, maybe something in the late time, but you will not have any change in the signal at the beginning. So I don't know if you have any intuition, maybe if this is just because of the one membrane that you have the trapping horizon, or I don't, just if you have some intuition. Why it is special for black holes?
No, not really. I mean, as I said, I think this is something that there's something to be understood here about why this is true. Mm-hmm. You know, I think we can look forward to getting, you know, this may really be a case where if we can get enough, or even just one very strong signal, you know, LIGO will come online again next year with much improved sensitivity compared with the first event. And so if we get another event as strong as the first one with the improved sensitivity, hopefully we can get even better measurements.
Okay, we have another question from Sebastian. I will just allow you to talk. You can unmute yourself.
Well, hey, could you hear me?
Yes.
Okay, well, thanks for this great talk. I have a question regarding the tests of the quasi-normal modes when they have been changed a little bit. So have the amplitudes all been varied when doing this test? So have there been, was there a new fit to also change the amplitude? Okay.
Yeah, so for each change, you do a complete and best fit.
Redone everything, and it's okay. This is great. And yeah. Thanks.
Yeah, and it doesn't fit as well.
Okay, yeah, thanks.
Okay, so we might actually stop here for 5 minutes, right? In the program, there is a short break, and then come back for a discussion with all the speakers of this first session. So just 5 minutes.